All right, so in the last video at the very end, I realized I was getting rushed by the timer. I knew it was going to end on me, so I made a mistake when I was evaluating those last couple tangent values. So we're going to redo that example, and we'll do one more with cotangent. So we're going to graph, again, negative tangent of 2x. So we're going to start with a table. And what we saw was the period for this one is going to be pi over 2. So what we really want to look at is values between negative pi over 4 and pi over 4. And that should cover, because that distance right there is pi halves, that should cover one full period for this tangent function. And then we also know that it's going to reflect over the x-axis. Okay, so we're going to start at negative pi over 4. Um, and then we're going to go to negative pi over 8, 0, pi over 8, and pi over 4. And we're going to evaluate by just plugging in. So we're going to use negative pi over 4 first. So that's the y equals the negative tangent of 2 times negative pi over 4, which turns into the negative tangent of negative pi over 2. And we remember from the tangent function, this is undefined because the cosine of negative pi over 2 equals 0. So we can't have any cosines equaling 0. That'll make this undefined. Right, and then for the next one, we do negative tangent of 2 times negative pi over 8, which becomes the negative tangent of negative pi over 4. And for negative pi over 4, we know all the pi fourths, they're the same. Sine and cosine, I mean, are the same. So you're going to get 1, negative 1, because you're in quadrant 4. But because there's also a negative attached here, this is the negative function, the two negatives will actually turn that into a positive 1. So this is negative 1 comes from this fact that this is in quadrant 4. This negative is attached to the function, so the whole thing will evaluate down to 1. And then if you did that again, negative tangent 2 times 0 equals the negative tangent of 0. And the tangent at 0 is just 0. That's where sine is 0. And then we could do the same thing for those last two values, but we should get 1, 0, negative 1, and then undefined again. All right, so if you compare that with the tangent function, the 1 and the negative 1 have kind of flipped places, but that should make sense because this is going to reflect over the x-axis. So all the positive y's for tangent have become negative y's, and so on and so forth. So let's do our graph. And what we want is this will be negative pi over 8, negative pi over 4, we pi over 8, pi over 4. And our asymptotes are at the pi over 4 spots. And we had 0. At negative pi over 8, it was 1. At pi over 8, it's negative 1. So this actually kind of looks more like the cotangent graph. And that, again, has to do with the fact that it's reflected over the x-axis with that negative y value out in front. Okay, and then again, our period has shrunk in half. Our period is only pi over 2 this time instead of a full period of pi. And then after that, it would just repeat forever and ever and ever. All right, so we're going to do a second example. So for this example, we're going to graph y equals negative 2 cotangent of x. All right, so no change in the period. This will reflect, again, over the x-axis. That has to do with that negative sign right there. So that'll make it reflect over the x-axis. The period will still be pi because the b value is 1. So we haven't multiplied the angle by anything, so it'll be its normal pi. So if you remember how we did cotangent, we went from 0 to pi. So we'll do that again. So we're going to draw one period on 0 to pi. But what has changed is that 2. So this is kind of an amplitude type of deal. Now, amplitude was I put quotes around it because it's not exactly amplitude, but it has stretched it out the same way that multiplying by a value in front stretched out the sine or the cosine function. So this will be amplitude of 2. It's not technically an amplitude because there is really no bound, right? There is no max and min, but it's that same type of deal. It's going to stretch by a factor of 2. All right, so we kind of know that's what should happen. Let's just check some values, plug it in. It's a really good idea early on as you're getting more comfortable with it. Plug in some values. Since our period is the same, we're going to plug in the same values that we did with the regular cotangent graph. So we did 0, pi over 4, pi over 2, 3 pi over 4, and 2 pi. And so what we get is when we plug in 0, we're going to get y equals -2 times the cotangent of 0. But remember, cotangent is the cosine of 0 over the sine of 0. And that's no good because that's going to make this undefined, right? We can't have sine of 0, which is 0. We can't have that happen. So this will be undefined. When you plug in pi over 4, you get -2 cotangent of pi over 4. And the cotangent, the pi over 4s are the good values. That's where it's just 1 because sine and cosine are the same. So what you get is -2 times 1, or just -2. So this will be -2. So that's kind of the stretch. We saw with the regular cotangent function, this value right here was 1. Now it's going to be 2 because of this 2 that you're multiplying every y value by. Pi over 2, this would be cotangent of pi over 2. And again, that's really, this piece right here is really the cosine of pi over 2 over the sine of pi over 2. Cosine at pi over 2 is 0, sine is 1, so that whole thing just boils down to 0. And then multiply by anything, it's still 0. We'll get a 2 here, and then we'll get undefined. So that should cover our full period. It's going to be stretched out a little bit by a factor of 2. So I'm going to have to go up to 2 now and down to -2 to graph this. And then we're at 0, pi over 4, pi over 2, 3 pi over 4, and 2 pi. And then this is where it should repeat. So every time you hit a integer multiple of pi, and that includes 0, then we're going to be undefined. At pi force, we're at -2. Pi over 2, we're at 0. 3 pi over 4, we're at +2. So that's that kind of vertical stretch that it looks like. And then same kind of deal. This one looks a little bit more like the tangent function, even though it was a cotangent function. But that's, again, because we had that reflection over the x-axis. So it looks a little more like tangent just got stretched out when you multiply by a negative. Okay, that is it for this video.